Yesterday I have completed the EIP-712 basics, wherein I got to know about how exactly EIP-712 works, what is domain separator, then hash type, hashStruct, the importance of Kitchak 256 hash, then the importance of salt inside the domain separator. So all those theoretical part has been completed yesterday. Today I'm going to implement the EIP-712 verify.solve smart contract using AI as a mentor or tutor. So let's get started with it.
Hi, let's begin today's session.
Welcome back. Before we dive into building EIP-712 verify.solve, let me quickly verify your retention from last session. So quick recall check. Last session you derived the complete final hash construction from first principles without looking it up. Can you write out the full final hash formula? What each component prevents?
Okay, the full final hash formula is equal to first
The prefix string x19 and x01.
it is concatenated with the domain separator, and then we have I think encode data of S.
What each component prevents, take your time. This is the foundation everything we built today sits on.
Okay, then the prefix prevents or informs EVM that it is not a transaction. It can never be
Executed on its own. Now I think this would be an overstatement. The prefix prevents or informs EVM that it is not a transaction. Domain separator
includes name, chain ID, version, then salt.
I think domain separator also has verifying contract. Verifying contract. This
Prevents signature replay attacks using same signature for EIP. I think it was 11 within same signature for EIP 1191 by the use of version, and if at all there exists multiple dApps with identical name, version, chain ID, and verifying contract, then they can make use of a random salt and salt of bytes 32, ensuring domain uniqueness. And at last we have encode data of S. This is nothing but Kitchak 256 hash of hashStruct, then typeHash. This again includes Kitchak 256 hash of S, where S is the structure. Then what each component prevents, take your time. Okay, I think I have answered almost most of it.
I think there might be issues with encode data. I think so. Good recall overall, but I want to flag two things before we touch any code. Small but important. Encode data is not the last component. Look at your own notes from last session. What is the correct third component and how does it relate to encode data? Issue 2, your encode data formula. You wrote this either nesting wrong. Let me ask you to untangle it. hashStruct is defined as, right, kcheck256 hash of type hash and encode data. Given that, what is type hash exactly and what is its relationship to encode data? Are they nested inside each other or concatenated? Okay, so typeHash is kcheck256 hash of the structure where if there is a struct, say struct transfer having address 2 and joint 256 amount, then its type hash is calculated as kcheck256 hash. Here we will have transfer address to showing 256 amount. So this is how type hash is calculated. What is its relationship to encode data? Are they nested inside each other or concatenated?
They are not nested but concatenated with each other.
They are not nested, they are concatenated. Good connection, but your type hash definition at the start was slightly loose. You said type hash, but that's not quite. Idam gave the correct example. So what is actually being hashed to produce type hash? Give me a precise one-line definition, not an example, a general definition. What is actually being hashed to produce type hash? Okay.
The structure name and its members are hashed to produce type hash.
Okay, got it. Correct. So more precisely, type hash is nothing but kcheck256 hash encode type s, where encode type of s is the string representation of the struct name followed by its members with its types. Now let's fix your final hash formula from earlier you had. Okay, so the correct formula is kcheck256, the prefix string concatenated with the domain separated, concatenated with hashStruct of s, where hashStruct of s is equal to kcheck256 hash of the type hash concatenated with the encode data of s. Two things were off in yours. You missed the outer kcheck256 and the third component is hashStruct of s and not encode data of s directly. Does this distinction make sense to you before we proceed? Let me go through it once. So we have the prefix string domain separator. This is the clear part. Then we have hashStruct of s and how hashStruct is calculated using kcheck256 type hash concatenated with encode data. Okay, so we have prefix string domain separator, then hashStruct of s, and hashStruct of s is nothing but kcheck256 hash of type hash concatenated with encode data, the encode data of s. Okay, does that distinction make sense to you before we proceed?
Yes.
Good. Now let's build. Before writing a single line of Solidity, I want you to think about the contract structure first. We need to build EIP-712 verify.sort. Based on everything you understand about EIP-712, what functions do you think this contract needs to expose? Don't think about implementation yet. Just think about what a caller would need from this contract. The caller would need domain separator. The caller would need domain separator. The EIP-712, the structure or the data format or signature submission, and a verify function. Okay, you said the data format for signature submission. What specifically does that mean in terms of a function? The user has signed some data off chain. Your contract receives the original struct data, a signature VRS. What does the contract need to compute internally before it can call ecrecover? Okay, you said the data format for signature where signature submission. What specifically does that mean in terms of a function? Think about it this way: the user has signed some data off chain. Your contract receives the original struct data, a signature VRS. What does the contract need to compute internally before it can call ecrecover? Internally, the contract needs to compute the final hash, which is given by before it can call ecrecover. Okay, exactly. So break that down into the internal building blocks the contract needs to compute. It needs domain separator, computer one-set deployment, cached in a state variable. It needs hashStruct of s, which itself needs the structure. Okay. Then it combines them into the final hash, then calls ecrecover. So question hashStruct of s is equal to kcheck 2 bytes of typeHash or encode concatenated with encodedata of s. For a concrete struct like struct transfer address to uint256 amount, what are the two things the contract needs to compute? hashStruct, and which one of those is a compile time constant in Solidity? It needs the below two things. First is typeHash, which is a compile time constant. It can be calculated using keycheck 256 and then passing the struct signature is 256 amount. So this is typeHash, which is compile time, and the data part, which is tool, and amount, which is dynamic, and it can be calculated at runtime. Okay, so now you can see the full picture of what functions the contract needs. Domain separator, computed once at construction, stored as state variable. hashStruct takes struct data, combines typeHash constant plus encode data. Verify takes struct data plus signature, returns recovered signer. Now before we write any code, one more important question. For domain separator, It is also a hashStruct under the hood. Okay, domain separator hashStruct EIP-712 domain, which means it also needs a type hash. For our contract, the domain will have name, version, chain ID, and verifying contract. What is a type hash string for this domain struct? Write it out exactly as it would appear in Solidity. Pay attention to field order, types, spacing, and no spaces after commas. What is a type hash for EIP-712 domain struct? It would be bytes 32 C712 domain struct is equal to kitcheck 256. Then we will pass on. Okay. Hashstruct EIP-712 EIP-712 domain. For our content, the domain will have name. So it is string name. Then I think version is uint8 or uint256. Let us verify that. EIP-712. Okay, version is also string. Then string version. This chain ID. Chain ID is uint256 uint256 chain ID. And then verifying contract. It has verifying contracts. What is the type hash string for this domain struct? Okay. So this is the type hash string for EIP-712 domain struct. That's the domain type hash, and yes, it's a bytes 32 constant. No need to recompute it at runtime. One small naming node convention in Solidity is okay, I've got it. Yeah, EIP-712 domain type hash. The type hash suffix makes it clear what it represents. Now we are ready to write the contract. Let's go step by step. Your first task, write just the contract skeleton, no implementation yet. Include the SPDX license and pragma, the EIP-712 domain type hash constant, the transfer type hash constant for this struct. Okay, so where should I write? I think I should use remix ID. That way you can a new tab, remix ADE. Click on launch the app. Then okay, so remix is loading. Click on the file explorer. And from the file explorer, create a new file. Name that file as EIP-712 verifier.so. So our first step is to use the SPDX license identifier. License identifier. I'll use MIT. Then pragma. Okay. Then pragma solidity. The current compiler is, let's check that, 0.8.34. So I'll use, let's say 0.cap 0.8.26. Then after this, what is the third step? SPDX license and pragma. First, this one is done. The EIP-712 domain type hash constant. So bytes 32 constant EIP-712 domain type hash is equal to kitcheck 256. We have EIP-712
Domain is the struct name. Then string name, string version, chain ID, address, verifying contract. Okay. So string name, string version, int 256, chain ID, then address, verifying contract. Let me just now copy this and compare both the statements. Are they identical? Okay. Let us select this. Yes, they are identical. And let me now remove the second part. So this too is completed. The transfer type hash constant for this struct. Okay. Transfers of bytes 32 constant transfer type hash, which is equal to catchat 256 hash of the struct transfer having member address to show in 256 amount. Step third is also done. The domain separator state variable as bytes 32. Okay, the domain separator state variable as bytes 32. So I think we can use domain separator as immutable variable because we can initialize the immutable variables inside the constructor. But I think we cannot do that because here the constructor accepts name and version as strings. So let me just declare bytes 32 public domain separator. Expected, okay. Wait. Only constant variables are allowed at file level. Why? Okay, so this will go inside the contract. Contract EIP-712 verifier. Then inside the contract, what's happening here? Public, we got public. Or it's a public. Okay. Domain separator. This is also done. Empty function stubs for hash, struct, and verify. Three function structs. Function struct, function verify. Okay, struct. Okay. Let me wait is full choice public. And verify also public. Done. After that, a constructor that accepts name and version as strings. So let us define a constructor that accepts name, string memory, version. Done. Don't implement anything yet, just the skeleton. What does it look like? So it looks like this. It looks like it's missing SPDX impact. No. Okay, Those are added on the top. hashStruct signature is incomplete. Think about what hashStruct needs as input for a transfer struct. What parameter should it accept? What inputs does? Okay, you got it. So first, issue 1, we already have added SPDX, license identifier and pragma solidity. Second, hashStruct signature is incomplete. Think about what hashStruct needs as inputs for our transfer struct. So hashStruct needs address, receiver, and here 256 amount. And then verify is incomplete. What input does verify need and what should it return? What a caller passes in and what they get back. Verify. So it will accept bytes 32 hash, then bytes 32b, bytes 32 on, and he will get yes. Now I think all are bytes 32. Let me just verify this with a Google search. What the data types of signature ARNS signature. AI mode VRNS components R is 32 byte, S is 32 bytes, and V is 1 byte integer. Yes, V is UED8. V is UED8. So V is UED8. Okay, got it. Size the data skeleton. Two things to refine. Receiver and amount that works, but these represent a transfer struct in Solidity. Got it. It's cleaner and more idiomatic to pass the struct directly. Got it. hashStruct. So it accepts transfer coordinator transfer. For that, the transfer struct must be defined. Trace tool showing to basics. Key public returns to bytes 32. K verify bytes 32 hash. Issue verify return type and parameters. Link returns an address. Let us verify. Think about what verify should return. There are two reasonable options. Return the recovered address and let the caller check it. Take an expected signer address, verify internally and return bool. Which approach do you think is more flexible and why? It should return bool. Return bool because the whole idea of verify function is to ensure the signature is valid. Thus, no point in returning the address, whereas returning bool makes its public returns bool. With that said, here is the updated skeleton. What's missing from verify is function argument address sooner. So this after adding that, the function signature becomes okay. Now the skeleton is solid. One last thing before implementation, look at your hashStruct and verify functions. Both are marked public but neither modify state. What visibility and mutability modifiers should they actually have? Both are marked public but neither modifies state. Your what visibility and mutability? Both are marked public but neither modify state. What visibility and mutability modifiers should they actually have? So regarding mutability, they should have pure, and regarding visibility can be external. So if you are asking should external contracts be able to call them, I think no. Contracts be able to call them, yes. The visibility can be external and mutability will be pure. Okay, but think carefully about hashStruct. You said pure, but hashStruct needs to compute domainSeparator as part of the final hash. But it actually doesn't. hashStruct only computes kcheck 2 by 6 hash of typeHash and encodeData transfer. But verify does something different. It needs to access domainSeparator to build the final hash. So domainSeparator is a state variable. Thus pure allow reading state variables. For verify, we should not use pure because we are reading state variable. So the correct mutability is U for verify. It reads state but doesn't modify it. Okay, and hashStruct is pure. It only takes inputs and computes the hash, no state access. Let me update that. hashStruct is pure, not public pure, external pure. And it can also be public or external. Okay, so hashStruct becomes external pure, and yes, verify becomes external view. hashStruct external pure, domainSeparator external view. That is what we have in our contract, external pure and external view. So the skeleton is now solid. Now let's implement. Start with the easiest piece first. Your task, implement the constructor. It needs to compute and store domainSeparator. Remember, domainSeparator
is equal to hashStruct of EIP-712 domain, which is keychat 256 hash of EIP-712 domain hash concatenated with name, concatenated with version, concatenated with chain ID, and concatenated with verifying contract. Name and version are dynamic types. How are dynamic types encoded in EIP-712? Got it. Name and version are dynamic types. How are dynamic types encoded in EIP-712? Dynamic types are encoded via keychat 256 and pass in the name and keychat 256 pass in the version, chain ID and verifying. I think chain ID is available via, can access it via block.chainid, and verifying contract is accessible via address of this dot contract. Let us look at Solidity documentation. Solidity read the docs. Okay, Solidity performance security. I'm not a bot. Come on. So here we have a section units and globally available variables. You just want to verify for chain ID. Let us search chain ID. Yes, here it is. It is accessible via block.chainid and the session's null case. So domain separator is hashStruct of EIP-712 domain. Okay, and EIP-712 domain is nothing but keychat 256. But before, how does concatenation works in Solidity? Let us take a look at an example. We will search keychat 256. Encode which selector, encode returns bytes, memory encode packed, performs packed encoding of the given arguments. Note that because echo is a way to compute the hash of structured data, although be aware that it is possible to craft a hash collision. Number of bytes, bytes.concat. Okay. Members of string. How to concat? The bytes can be concated using bytes.concat. But the real question is how exactly this works. I mean, this concatenation part, how is that done in Solidity? Let us go to Google AI, move on Google. Give me an example of AI mode. Come on, search it fast. Okay. I hope this is clear. The keychat 256 hash of the signature string. This is concatenation true. All 532 blocks are concatenated into a single 160 continuous byte array. For this is ANC. Do we have ANC inside Solidity? Final hashing, got it. In Solidity, instead of this, I can ask any pins for performing concatenation inside Solidity. Can I directly use PLC
followed by the data type, data value,
Okay, yeah, this one I missed. It's address of this, not address of this dot contract. For concatenation, you use abi.encode. Okay, got it. It's simple. abi.encode. Now write the constructor using this pattern. Plug in all 5 components in the correct order. So let us go to the constructor. This is domain separator, hashStruct of EIP-712 domain, which is nothing but key check. Let me copy this.
Shell Linux.
Let us paste this above constructor so we don't miss the order. And then name and version of dynamic types, our dynamic types encoded.
Got it. Domain separator equals keycheck 2 by 6 hash abi not encode. So first is name,
Value 1, value 2,
value 3. First is name, then we have version, then we have block.chainid, then we have verifying contract, which is address of this.
Let us give this. Now write the constructor using this pattern. Plug in all 5 components in the correct order. 1, 2, 3, 4. Which is the 5th component? Yeah. We have
We missed this one, domain typeHash. So first is
now the constructor is complete.
we copy this.
Oh, no step, but there's one subtle mistake. You are passing name and version directly. Oh, my bad. Into abi.encode. But remember what you said earlier, dynamic types like string are encoded as keycheck 2 by 6. File
Keycheck 256 of name,
invalid type or argument in function call, invalid implicit conversion from string memory to bytes memory. This function requires a single bytes argument. Use abi.encodePacked.
key API to encode fact. Should we pass in name? So name, similarly we will use for version.
Done. It won't produce a 32-byte value, correct? It will encode the full tree in line, which breaks EIP-712 spec. How should name and version be encoded before passing them in? But let me ask you one thing about your choice of abi.encodePacked for the strings. Both give you the raw bytes of the string. In fact, for a single string argument, the more idiomatic way you'll see in production code like OpenZeppelin is simply bytes name. Both are correct, just worth knowing so you recognize it when reading other implementations.
But okay, got it. So if we directly use name,
In that case, it says invalid type for argument in function call, invalid implicit conversion from string memory to bytes memory. So we convert names to bytes. That fixes the earlier cited issue. Hence, here also we are going to use bytes. Constructor is complete and correct. Now implement hashStruct. Remember, hashStruct of transfer is equal to check 256 hash of transfer typeHash concatenated with transfer.to and concatenated with transfer.amount. To and amount are atomic types. How are atomic types encoded in EIP-712 and what do you use in Solidity to concatenate them? I think we will use abi.encodePacked.
Yes. hashStruct. So return
check 256 hash. First we will give a transfer type hash.
Then abi.encodePacked. So we will give rod capital transfer but transfer.to print transfer.amount.
Something is wrong. Wrong. Argument count for function called. 2 arguments given but expected 1. Okay.
abi got encode backed. So we can catch at 2 bytes its hash. 2 arguments but expected 1. Okay, missed one thing, abi.encode. And inside abi.encode, you will add typeHash. Let me just try adding directly transfer.to. Then we add transfer.promote.
2 and amount are atomic types. How are atomic types encoded in EIP-712 and what do you use in Solidity to concatenate them? Use abi.encodePacked in Solidity
To concatenate atomic types.
but there's a mixing issue here. You are using abi.encode on the outside and abi.encodePacked on the inside. This is an incorrect. abi.encodePacked produces raw packed bytes, but when you pass that as an argument to abi.encode, it gets encoded as a bytes type, not as 2 separate 32 byte values. Think about it this way. EIP-712 says each encoded member value is exactly 32 bytes. abi.encode naturally pads every value to 32 bytes. abi.encodePacked does not. So the question is, should you use abi.encode or abi.encodePacked for the outer encoding and why?
So the question is, should you use abi.encode or abi.encode backed for the outer encoding and why?
Since EIP-712 says each encoded member value is exactly 32 bytes, abi.encode. For the outer encoding, because EIP-712 says each encoded member value is exactly 32 bytes. So remove the inner abi.encode and pass all values directly into a single abi.encode.
Okay.
Now implement verify. This is where everything comes together. Remember what verify is to do. Build the final hash ecrecover 256x19, the prefix string concatenated with the domain separator, hashStruct of transfer. Okay, first we will build the final hash.
Bytes 32 final hash is equal to check 256. Now since
We want to use concatenation, so inside check 256 we will use abi.encode, because abi.encode, as stated earlier,
abi.encode
naturally pads every value to 32 bytes, and EIP-712 says each encoded member value is exactly 32 bytes. Hence we are using abi.encode, and in abi.encode, for calculating the final hash, it is a combination of the prefix string, domain separator, and hashStruct of transfer. So let us add the prefix string first. Prefix string,
which is \x19 and then \x01. This is the prefix string. This is concatenated with the domain separator.
We have already calculated the domain separator inside the constructor, directly using that over here. And at last we have hashStruct of transfer. Now hashStruct, this is our function. We have set this function, we have set the visibility of this function to be external. So in order to call this function,
but hashStruct of transfer, right?
you build the final hash, hashStruct of transfer.
Okay, so it is again abi.encode. We can call this function using this dot hashStruct, but don't, in the verify function, we don't have transfer, right? So how can we call this?
You are passing a pre-computed hash, but should the caller be computing the hash externally, or should verify compute it internally from the structure data? Think about what's safer and why.
To build the final hash,
You are passing in a pre-computed hash, but should the caller be computing the hash externally?
the hash must be taken inside the function.
They could pass in any hash defeating the entire purpose of EIP-712. So verify needs to accept the raw structure data, not a pre-computed hash. Update the verify signature to accept the transfer struct instead of bytes 32 hash, then implement the full function body. Now we can, because we were stuck over here, right? How to get this transfer? So we will remove this bytes 32 hash and pass in transfer call data transfer.
What does it say?
Okay.
Because in this way, we will calculate the final hash.
For the x19, x01 prefix in Solidity, it's represented as and we'll need abi.encodePacked here specificity is used for this final step rather than abi.encode. Why abi.encodePacked is used here rather than abi.encode? Okay, here abi.encodePacked is used because there's no need to represent the prefix string as bytes 32 added with zeros. It's just 2 bytes. Padding it to 32 bytes would change its meaning entirely. Okay, so instead of the encode, we will use abi.encodePacked. Final hash is write the full verify implementation. So first, the final hash is built. Call ecrecover with that hash and the signature component. Address original signer is equal to ecrecover hash is final hash, and we are passing the VR as component. Compare the recovered address against the expected signer, return true or false. So return original signer is equal to the passing sign. None. Sure, let me paste this. Here you go. The implementation of verify function. So we can use hashStruct or declare it as an internal function. This to keep it internal. So change hashStruct to internal pure. No, this function will be the external function and then directly call hashStruct. By making the visibility of hashStruct function to be internal and then call in this using the below approach. Okay, so EIP-712 verifier.sol is completed. So what we have done is, initially we have declared EIP-712 domain type hash. How is that calculated? Simple. Then transfer type hash, domain separator. Domain separator is set inside the constructor. Then we have made use of the verify function. So in verify function, we have calculated the final hash. After the final hash, we have called ecrecover on the final hash, passing in the signature component, and we have returned if the original signer returned by ecrecover is equal to the signer passed in to the verify function argument. If both of those match, then return true, else return false. Then hashStruct function. Here we are computing the type hash of transfer struct. Now let's put the complete contract together. Here is what you have built. Created a file read. Okay, before we write foundry tests. Oh, we will be writing foundry tests as well, right? So I will have to move the contract to a local directory. And what does that mean for if you passed it an invalid signature, what does it return? Is there a case where this could return true unexpectedly? Original signer, a return original signer is equal to signer. And what does that mean for your current implementation? Okay, good. ecrecover never rewards. If you pass it an invalid signature, what does it return? It will return address 0. And what does that mean for your current implementation? Okay. Yes. Let me verify what does ecrecover return. Does ecrecover return when the signature is invalid? I think address 0. Okay. Yes, good catch. So here, if somebody passes an invalid signature and passes a signer to be address 0, since the signature is invalid, ecrecover will return original signer to be address 0. And then in that case, since the signer is also passed in as 0 address, so this will return true. So we will have to put a check require signer is not equal to address 0. Invalid sign. Yes. It will return true. Yes, it will return true when signer will be address 0 and an invalid signature will be submitted. To address that, here is the updated approach. Okay, returns address 0 on ecrecover returns address 0 on invalid signatures. So if signer were address 0, the check would pass for any invalid signature. The require guard closes that role. Now let's write the Foundry test. Before you write any code, tell me what cases should we test. Think about the happy path, edge cases, attack scenarios we discussed in session 1. Happy path. The path could be valid signature, returning valid verify values, and invalid signatures, returning false, passing signer address 0, returning or reverting the transaction, edge cases, the clear protection, tests, passing the same signature twice, cross contract replay. What happens if someone deploys a second verifier with the same name and version and tries to replace signature from the first contract on it? This is something your domainSeparator should prevent at and worth going in a test. So our full test list is valid signature returns true, invalid signature returns false, enters 0, signer rewards, same signature submitted twice. What should happen? It should revert. Cross contract replay, signature from contract A rejected by contract B. For test case 4, same signature submitted twice, Should verify return false on the second submission or should it revert? Think about what your current implementation does. Does it have any replay protection built in? The current implementation doesn't have any replay protection built in. While it answers, let me go to terminal. So sure, let me create a directory encodeData of trade value. She is directed to copy trade value. Inside, I'll have to make this directory. So I'll have to make this directory a foundry directory. How can we do that exactly? So what needs to be added to prevent replay? Think back to session 1, you mentioned a specific mechanism. Nonce must be added to prevent replay of the same action. And nonce will be, so we need to add nonce tracking to the contract. Think about what changes are needed. Where do you store nonces? What data structure? Where do you implement the nonce, before or after verification? And why does adding a nonce change the transfer struct? Why? Answer these 3 questions before we write the code. Where do you store nonces? What data structure? Nonces can be stored as a state variable. Data structure that we can use is mapping from address 256 public nonces. Where do we increment the nonce, before or after verification? Increment the nonce after verification. Does adding a nonce change the transfer struct? Why? Increment the nonce after verification. Does adding a nonce, yes, to change the transfer struct, because hash struct of transfer must also take into account nonce apart from two NMR to prevent replay action. Instead, increment the nonce after verification. Think about this carefully. If you increment after verification, what is the sequence of operations? Verify signature, increment nonce. Now consider what value of nonce was used during verification in step 1. And after incrementing in step 2, if the same signature is submitted again, what nonce will be used in verification? Okay, now consider what value of nonce was used during verification in step 1. Okay, in that case, if the nonce was initially 0, then nonce 0 was used. And after incrementing in step 2, okay, in verify signature, the what value of nonce was used during verification in step 1? It will be 0. And after incrementing in step 2, if the same signature is submitted again, what nonce will be used in verification? Not quite getting the pursuit. Quite getting the question. Say Alice's current nonce is 0. She signs a transfer with nonce 0. First submission, contract verifies signature using nonce 0. Then contract increments nonce to 1. Second submission, contract verifies signature using what value? Current nonce is 0. She signs a transfer with nonce 0. Contract verifies signature using nonce 0. Contract increments nonce to 1. Contract verifies signature using nonce what value? The attacker submits the exact same signature again. What nonce does the contract use in step 1 on the second submission?
Can use nonce hand. Exactly, and Alice's signature was created with nonce 0. So verifying it against nonce 1 will pre-easy recall.
Later a different address and verify return false. So incrementing after verification actually does work for replay prevention. But now think about this. Should verify be the function that increments the nonce, or should nonce incrementing happen in a separate execute function? Think about the single responsibility principle. Verify currently just returns a bool. What happens if you add state modifying logic to it? Okay, what it?
Let's call the single responsibility room. Verify is now complete. Thus, incrementing nonce must be moved to a different function. But we will invoke this function.
In a real protocol, EIP-712 verifier would be a base contract, something like a vault or a DEX.
Book inherit from it. The flow would be
User submits signature to the outer contract, example copy trade vault. Outer contract calls verify to check the signature. If valid, outer contract executes the action and increments the nonce. So the nonce increment lives in the caller, not in verify. Got it. But for our standalone EIP-712 verifier.solve, we need a way to demonstrate this. So let's add an execute function that calls verify internally. If valid, increments the nonce and emits an init. Okay, since execute modifies state, what mutability does it have? And should it be external or public? Also, what event should it emit and what data should the event contain? Let us add a function execute
function execute should be external function since it will be called from outside the contract. This function internally calls verify. So if it calls verify, it must also expect these parameters, which it will pass on to the internal verify function. To execute if valid, increments in which element. Setup calls verify internally, so we should also change our verify function to internal and then require verify call with transfer and the signature component. Verification field And we should add a data structure mapping address to Shield 256 organic Nemesis. Since we can have named mapping as well, so address account and nuts. However, if this require statement passes, then it should increment the lenses of Scilab was equal to R. And then we will commit an event executed address signer Shield 256 Nonce. I think we will have to store nonce ampersand nonce equal to nonces of signer, because this will be the value which will be used by the signer or sign in, and we should emit that. Okay, done. Here is the final contract. By the time Claude reviews it, let me look about Foundry Project initialization. So initialize a new project, forge init. Let us do that. So cd space dot minus rf copy trade value, and then I'll run this command forge init. Pass in the project name, copy trade value. So initializing, while it completes initialization, let us go back to Claude. Great structure, but I see a critical issue. You added nonce tracking by the transfer struct. Okay, got it. Let me add the nonce to the transfer structure. And 256 nonce and hashStruct. So test is completed. ls, okay, one main branch. So Foundry project has been initialized. Let me open this in VS Code. Was closed. So file. Let me open a new instance of VS Code. So we have initialized a Foundry project. Now inside this Foundry project, good, you added nonce to the struct and hashStruct, but you missed the second thing. Got it? Transfer typeHash.
So transfer type hash, then the third parameter SUN256 nuts. Okay. Updated the transfer type hash. What does that mean for signature verification? Let us have a look at signature verification. So we have execute, verify, signer, transfer, encode packed, domain separator, hashStruct transfer. What does the struct now has 3 fields on the type hash, still only has 2. What does that mean for signature verification? Updated the transfer type hash, and now everything is at best of adding a nonce for preventing replay actions. Should we execute? Look at this sequence. Acquire, verify, signer, transfer, verification failed. Alice signs a transfer with nonce 0. When verify is called, it computes hashStruct using transfer.nonce, which is whatever Alice passed in the struct. Okay, but who ensures that transfer.nonce matches the contract stored nonce sign? Got it. Right now, nothing checks this. What could an attacker do with this gap? So, we also have to ensure require nonces of signer is equal to transfer dot nonce is nonce stored match, or we'll say invalid nonces. Invalid nonces. We get this. But who ensures that transfer.nonce matches the contract stored? I think checks. What could an attacker do with this gap? The attacker can use the same nonce multiple times, and the contract he'll verify that to be true. And yes, without that check, an attacker could reuse an old signed message with nonce 0 forever, since nothing was validating that the submitted nonce matched the contract's expected nonce. Here is the final complete contract. Do you know which cheat code produces? We open this. Cancel. Now let's write the foundry tests. Before you write any code, one question in the foundry test. So we'll stop here, and in the next session, we'll continue the foundry tests.